In this video, I'm looking at how to do optimization problems using the second derivative. So whenever we start an optimization problem or a worded problem, we want to draw a diagram if we can and define the variables. So what we've got here is a question where we've got the maximum area of a rectangular field that can be enclosed by 100 meters of fencing. So if we've got our rectangle, obviously we've got our length and our width. We know that our area is going to be length times width, but we also know our perimeter is going to be 2 lots of length plus 2 lots of width. That is what we can then use the 100 meters to try and work through our problem. So we've got 100 is equal to 2L plus 2W. So then we can write that 2L, and you could go with the width if you wanted. It doesn't matter which way you go. 100 take 2W. So then we would have our length is equal to 50 take W, because we can divide each of them by 2. We can then put that into our rule for area. So we've got area is equal to 50 take W times W. So we get 50W take W squared. And like I said, you could have gone with using the length instead and worked it through that way. Both will work. We want to find out when we want a maximum area. So that's leading us into our finding a stationary point, finding when that is equal to 0, and then solving for that and checking if it's a maximum or minimum. So when we do A dash, we're going to get 50 take 2W when we do our derivative. So we want to find out when that derivative is equal to 0 to find our stationary point. So 2W is equal to 50. So our W is equal to 25. So we can then go and, because we just want to know the area, we haven't been asked for the length and width, so we can sub that straight back in and work out what the area will be into our 50 minus W squared, or 50W, sorry, 50W minus W squared, and we're going to get 625 meters squared there. We want to try and test if it's a maximum or minimum. Obviously we could put this into our calculator and look at the shape of that, and we would see that it is the turning point is a maximum. Our other option that we have is doing our A double dash. So if we've got 50 minus 2W, we're just going to be left with negative 2. So not overly helpful in determining, we can't sub in that value of 25 to check if it is a maximum or minimum. Our other option, if we have that kind of case, is just to go into our A dash and sub in 24 and 26 to see what is happening either side of that stationary point. So when we put in our 24, 2 times 24 is 48, 50 take 48 is going to be 2, and then we will get a negative 2 when we do the 26. Because 26 times 2 is 52, 50 take 52 is negative 2. So we can see that when we've got our curve, when it's at 24, it's coming up. At the 25, we know it's 0, so it's going across, and then coming back down, which is our shape of a maximum. So our maximum area for that one is 625. We probably should have defined our variables up here of length and width for the L and W that we were using. The next one is a little bit less standard. The first one is probably one that you would have even seen that type back when you first learned derivatives, even back when you were doing quadratics. You could do it without knowing the second derivative. Here we've got that 2 positive numbers add to give 4, and we want the cube of the first plus the square of the second to be a minimum. So I'm going to use A and B as my numbers and start putting down this into some equations. So we've got that A plus B is equal to 4 is the first equation that we have, and then we want to find when we add those two. So I'm going to use T for total. I could have used S for sum, but S looks like a 5 and I don't like to use that. So when we add A cubed plus B squared, we're going to get the total, and we want to know when that is a minimum. So we will obviously want to go through the process of finding the derivative and testing with the second derivative. So what we need to do is first change this equation to get either A or B on its own. because I'm going to square or cube one of them, I'm going to go with the b because that one's easier to deal with. So if I've got b is equal to 4 take a, then I can put that in here and only have to square it rather than having to cube it. So I've got a cubed plus, and then I've got 4 take a squared. So I know that that's going to give me 16. And then I've got 2 times 4 times a, so minus 8a plus a squared will be that one. Collect and just putting them, so there's no like terms to collect, but I just like to put them in order from smallest to biggest to smallest in terms of power, highest power to lowest power, and we get our equation there. So first step, we're going to do t dash to then be able to find some stationary points. So that's going to give us 3a squared plus 2a take 8. Obviously we've now got a quadratic, so we'll need to factorise that. So our AC is equal to negative 24, our B is equal to 2, so we want two numbers that will multiply to give negative 24 but add to give 2. So if I do 6 and negative 4, that will work. So I'm going to pop that back in here, 3a squared plus 6a take 4a take 8. Factorising the first two terms, so I'll take out 3a outside of a plus 2. And then here I can take a minus 4 outside, and then I'll get an a plus 2 in the bracket there. I've got the common bracket of a plus 2. I'll bring that to the front, and 3a take 4. So now I'm trying to find out when that's equal to 0, which is my whole reason for factorising it. So I can say that a plus 2 is equal to 0, or 3a take 4 is equal to 0. If I have a plus 2 is equal to 0, I get a is negative 2, and then 3a is equal to 4, so a is equal to 4 on 3. Now, once we get this negative 2, we go back to our original statement that a and b are two positive numbers. So that means we can't have the negative 2. So then we're focusing on the 4 on 3. So then the next step is that we can either sub that back in now and get what the b is equal to. So we know that b is equal to 4 minus a. So we'll have 4 take 4 on 3. And we will get 8 on 3 as our answer for B. Then we want to test the second derivative to check if it is a minimum. So if we've got our t dash is 3a squared plus 2a minus 8, then t double dash is going to be 6a plus 2. So when we sub in our 4 on 3 there, we've got 6 lots of 4 on 3 plus 2. So our t double dash of 4 on 3 is going to be equal to 10. Now 10 is a positive number, which means that that is a minimum. We could also, like I said on the previous one, is put that equation into our y equals, graph it, and check that point there is a minimum as well. But obviously these kind of questions, if you're using this process, will probably be classed as tech-free. So you won't have your calculator. If you're an external, you won't, if this type of one is in there, you won't have access to your calculator. If you're doing an internal one and you have your calculator, obviously you can check.